to us. If you have any questions, we'll be around the room. Thank you. Over to you, Sridhar.
Okay. All right. Hello. Are you guys able to hear me okay? How about on the other room? Can you check it? Hello. I don't want it to be too loud when I get excited. Sorry. Hello. Better? How about in the other room? Are you okay? Good. Okay. Hi. Good morning, everyone. It's good to see a full crowd here. I heard there are more than 160 participants, which is good to see. CXL has been, since it was introduced 3 years ago, has been seeing a lot of industry excitement, and it's only growing. So it's very apt that we are having a tutorial session on CXL at this VLSI conference. So good morning, everyone. My name is Sridhar, and I work in the I/O standards group within Intel. I have more than 2 decades of experience, like was said earlier. And most of it is on I/O standards. Currently, I work on CXL. I work on the fabric sub-team, if any of you know. I work on that, and then UCAE, which is a new industry standard interconnect for die-to-die. So I work on that as well, and also PCI Express. So I have a ton of I/O-related expertise within Intel. And I want to first acknowledge Ishwar, who is my colleague. I saw a bunch of these slides for him. I'm stealing with pride because many of the foils that was presented at the HICC conference, I pretty much taken and repurposed here. So I want to thank him first. So this tutorial session is actually split into 3 different parts. I'll be handling the overview session, and then Sunita will be handling the more detailed deep dive on cache coherency and memory expansion and memory pooling. That will be coming down later. So mine will be approximately 45 minutes. I'll go through the foils, and then I would like to leave about 10 minutes at the end of the session for taking questions and answers. Okay. That's the way it is going to be. Before I get started, I would like to understand from the audience, how many of you have heard about CXL or just have a very peripheral understanding of CXL? Don't be shy. You don't have to be shy. If you don't know, it's fine. That's why you have the tutorial session. How many of you have a decent understanding of the protocols of CXL? Okay. So most of you are somewhere in between, it looks like. So I'll handle the foils appropriately. I'll focus more on the introduction, etc. Okay, so let's get started. This is pretty much the agenda. I'm going to just walk through the hall just to cover the full audience. So if there is some, someone test it out first. Okay, so this is the agenda. We'll go over the CXL release timeline, and then an overview of what the CXL protocol was intended to do, what are the different protocols, the stacks one level down, and then more interestingly, from an overview perspective, what are the usages CXL was intended for, right? I think it's good to get ourselves grounded on that. And then we'll go over the feature evolution. And now, since it was introduced in 2019, there has been quite a bit of definition of features, with the individual spec releases. We are at 3.0 right now. It was just released last year. So we'll go through the feature evolution of 2.0 and the 3.0, and then some exciting new things are coming up. Specifically CXL Fabric. This is the work that I'm heading right now in the industry. This is CXL Fabric, what it is, what are the usage models, and why is the industry so excited about it. We'll look at some of the use cases that are driving a lot of excitement, and then we'll have the summary and the question and answer session. Is there an issue in the other room? Okay, all right. Okay, so let's get started. Okay, CXL. Before we get into the details about the CXL at an industry level, you can see there are more than 180 member companies. Okay, there is a lot of momentum around CXL in the industry right now, and you can see all the big names in the industry in the CXL board of directors: AMD, Google, Intel, Meta, Microsoft, pretty much the who's who in the, especially in the cloud sector, right? You'll see all these companies are there as members of the board, and there's a lot of excitement. I'm personally very excited about working on CXL. So since this talk is around the introduction and the evolution, let's get through a quick timeline of how this thing got started and where it is today and where it is headed into the future. So this was introduced now 4 years ago, approximately 2019. CXL 1.0 specification got released, Intel released it, and then post that the industry CXL consortium was officially incorporated in September, about 6 months after the 1.0 spec was released. The board was formed, the consortium was formed, and then the 1.1 specification was released. And this specification was pretty much the 1.0 that was initially released for accelerator attach and a few other use cases with some additional erratas and others, right? So that's why you see 1.0. And then once the industry members got on board, there are some feedback that was received to make it better. And the initial 1.1 spec was released in September 2019. A year later, the 2.0 specification was released with a bunch of interesting upgrades that I will talk about, and also Sunita will talk about, primarily around switches and memory pooling, etc. So that was in November 2020. And then middle of last year, we released the 3.0 specification, and that had a whole bunch more upgrades, okay? Much of it targeted toward data centers. You will see a lot of the feature evolution of CXL around the data centers, cloud usages. That's why you'll see a lot of cloud company CSPs, that is cloud service providers, are a big votaries of CXL, and they are contributing a lot. Okay, can we allow people only through that group? Done? Okay. Okay, so around Q3 of or middle of last year, we released the 3.0 specification, and we are getting ready to release a 3.1 specification sometime this year, first quarter, the second quarter of this year. And I'll talk a little bit about the work that's happening around that. And it's got to do with fabrics, software-defined data centers and things of that sort. Okay, so we're getting ready to release the 3.1. And this is roughly the timeline for how CXL got started and where it is today. Okay, so a quick overview. So what is CXL, right? So CXL is this new breakthrough high-speed interconnect, and it is allowing heterogeneous compute in your platform, right? So previously, your CPU and the GPU, the XPU, were in their own domains, right? There was not a lot of fine-grained, compute collaboration between these compute nodes, and also there was no standard mechanism by which you can expand memory beyond what the processors allow. Okay, so the CXL interconnect provided new ways to allow the CPUs and the GPUs and the XPUs, all the accelerators that you can put on the PCIe slot, for example, they can work collaboratively in a cache coherent fashion. And the details of this, Sunita will cover later. So this is a cache coherent interface that allows the CPUs and the accelerators to work in a much more fine-grained fashion, collaborate in a much more fine-grained fashion, and it also allows for memory expansion on an industry standard interconnect, which we did not have before. And this is very exciting because, I mean, this has been talked about, from the time I joined the industry 2 decades ago. We've always in some form or other talked about doing this kind of stuff, but only now it is materializing. All the right set of things are coming together to make this viable at this stage. Okay, and it's very interesting because the cost per bit of a DRAM is happening up, right? It is not reducing because of the economies of scale of building DRAMs. So you want to use your memory in a much more efficient fashion. And so CXL allows you to do that, and we'll see a little bit, and you'll see more details of it as Sunita will talk about it later in our session. So, and it builds on PCI Express PHY and the electrical interface. Okay, so PCI has been there for more than 2 decades now, and it has a very big ecosystem built around it. So we want to leverage, or we are leveraging the PCI physical and the electrical layer, and the CXL protocols run on top of the electrical layer. So we get that leverage from PCIe. We don't want to reinvent the wheel, and that's what we are doing here. And more importantly, it is delivered as an open industry standard. If you see a big reason for why PCIe is so popular is because of the wide acceptance in the industry, right? So there's a lot of horizontal solution building in the industry. Not everybody is doing everything, right? People who are good in CPUs are building CPUs with the PCIe, car builders are their own stuff. So this is the horizontal industry, and the big reason why PCIe is successful is because of that, right? It's an open industry standard. CXL is that. That's why Intel released this as an open industry standard in 2019, and it has grown big ever since. And right now we are at 3.0 as we saw earlier. And we will continue that. As I said, there's a lot of momentum building. There is a lot of new ideas, okay, on where to take CXL. And some of these ideas are coming to bear in the CXL 3.1 version that's upcoming. And we are already starting to talk about CXL 4.0 and what we want to bring into CXL 4.0 a couple of years ago. Okay. All right. So if you go one click down and then look at, okay, all right, fine. CXL is an industry standard cache coherent interface, but how does it look at look from a platform perspective, right? So if you look at a processor with a PCIe interconnector today, right? You have PCIe port coming out of the processor, and you on the platform, let's say you have a 516 connector. Today you can plug in a PCIe card. We all know how that works. So on the same connector, we should be able to plug in a CXL card as well. So if you take a standard Intel accelerator or an NVIDIA accelerator, a GPU, and you want to plug that card into, you should be able to build a card that plugs into the same 516 PC connector, and it should work. And so this is called as a flex bus port, in the sense that on the same mechanical footprint, you're able to plug in a PCIe card or a CXL card, and the processor is able to figure out through what is called as an alternate protocol negotiation. Okay, so when the card at power on, either side is able to detect what the other side is capable of doing. So if this processor is capable of CXL and the card is capable of CXL, they both negotiate with CXL. If one side is capable of only PCIe, the link that comes up to be a PCIe. So we want to take the ecosystem that is already strong and popular, and then we want to enable CXL on it. That's why this is built up to be a flex bus protocol with alternate protocol negotiation enabled via these links. Okay, and CXL 2.0 and 1.1 are at PCIe Gen 5 speeds, 32 gigatransfers per second. The 3.0, which was released recently, 2 quarters ago, is aligned to PCIe 6.0, which is 64 gigatransfers per second. And it is fully backward compatible. Yeah, this is the other thing that you need to know. Backward compatibility is like a baseline requirement as we evolve the specification. That is, as we go to newer and newer versions of the specification, we want to preserve the investment that the industry already has built around building solutions for earlier versions of the spec and not make it obsolete, right? And that will really kill the ecosystem. So we want to make sure that we evolve the CXL specification in a way that it is backward compatible. For example, let's say your processor moves faster and it's building solutions for 3.0. It should still work when you take an older card, a 516 CXL card, and you put that into the same slot with a processor that has newer capability. So we want to enable this backward compatibility, and we pay extra attention, just like in PCE. This is nothing new from CXL perspective, but it is an important trait, okay, for the ecosystem to move forward. Okay, on the one click down on the protocol. So okay, when we talk about CXL, what do we actually mean beyond what is visible at the platform level? If you look at what is required to complete a full CXL stack, so there are 3 different protocols that we are enabling on CXL. So when we say CXL, there are 3 sub protocols, okay? And we will have a foil. We have a foil later down that talks about which use cases need which of these 3. Okay, so there is a CXL.io, which is a standard. Think of it as PCIe. Whatever you see in PCIe, if you're aware of PCIe, what it does today, we are calling it a CXL.io. It's required for discovery, configuration, enumeration, interrupts, error handling, and regular DMA. So devices are built to be non-cache coherent. You want to do regular DMA between host memory and your device. And that's where you use the CXL.io. And then the new additions are the dot cache and the dot memory. These are separate protocols. These are all individually negotiation when the CXL link comes up. Okay, so the CXL.cache is for the scenario where, let's say, the device is trying to, okay, in this particular picture, so the device could have its own cache here. Okay, in the lot, the CXL device, think of there being a cache, and the cache is actually caching the DRAM that's connected to the CPU. Let's say there is, okay, so let's say this host DRAM, right? The device reads the host DRAM and puts it in its cache. Okay, so but you want to be cache coherent with the CPU caches and CPU memory and all that. So what protocol enables that? That is a CXL.cache. So the device caches the host memory. You use the dot cache channel to maintain cache coherence. The dot mem is for the case where the device itself has some memory. Okay, previously in PCE land, this memory is all proprietary and device specific, right? It's not part of the coherent cache memory that the CPU or the OS sees, right? The OS sees only used to see only the memory attached to the CPU socket as cache coherent DRAM. But now we can enable enable portions of this optional device memory as being cache coherent. The CPU can read this memory as if it is reading its own local memory in the CPU, okay? And it can cache in its caches. So to enable that to happen, we have a separate channel for the CXL document, okay? Processor access to device attachment. So these 3 protocols in turn comprise the CXL protocol overall, okay? And we have one click down. What does it mean from a microarchitecture level? We'll see in the next step. So pictorially that is shown here, right? So you see a host, and then you have a bunch of cores, and then there is coherency and memory logic, and then there's a PCA logic. All of these 3, when you support them over CXL, all of these 3 get muxed out into the same PCIe PHY and logical PHY. Okay, all these protocols run on the same individual virtual channels, if you may, but individual queues, for example, they run on the same PHY. Similarly, on the device side, you have the same bus, and then this memory channel is used for CPU access to this optional device memory, and the cache channel is used for the device accesses to the host memory. Okay, and the PCIe IO.io or PCIe is used for regular stuff like discovery, configuration, DMA, etc. Okay, and all of these things are dynamically multiplexed on the same physical pins. Depending on what format, what protocols, sub-protocols that the devices on either side support, all of these 3 could be running at the same time, and they are dynamically muxed on the same physical. Okay. Okay. So if you look at it from a microarchitectural perspective, um, are you not able to hear?
We are seeing the upcoming slides as well.
Yeah, no, it should be.
Okay. All right. Okay. Looking at it from a
CXL board to XL, that will train to XL. In what way the CXL board to behave because it cannot use cache. So
just like a PCA link today. It's just like a PCA link today. So that there is no coherent memory on the other side of the link. So the device cannot access cache what it reads from the CPU. Similarly, the CPU cannot also cache what it reads from the device memory. It's all uncacheable semantics.
So where does the break happen? It's still there. So because the board is now it's a big set, but the one controls the one. Suppose this is the configuration. We want to be something from this side. This side, the both side, the one is controlling CXL board. Will issue those parameters. But where will it exactly break? It will not go on the big set because there's no order.
So just hold on to that. It could get covered in subsequent slides. Otherwise, we'll take it towards question and answer session. All right. But to quickly answer the question, the memory on the others in the device side will be marked in the CPU page tables as uncacheable, which basically means that any CPU access to those memory will not go through the CXL dot cache channel, mem channel at all. So it'll be like a regular PCE, like it happens. Like regular MMIO reads and writes. That's how in hardware it is all ensured. Even once you mark the page tables as uncached. Okay. So microarchitecturally, if you want to look at it from the higher level picture we saw earlier, see, so this blue thing, right, is the PCE stuff that we all know today, the industry knows today. Okay, so that is still maintained. Okay, for the reason that we talked about earlier, which is you could plug in a PCI device on the other side and the protocol will negotiate to PCIe. So when that happens, only this blue portions of this picture is active. Whatever we know of the PCI protocol will be active. There's nothing more, nothing less. But once the device on the other side is capable of, let's say, CXL, CXL.io and .mem and .mem, just to make the discussion simpler. Let's say it's capable of all these three. Then this green portion of this logic will be negotiation. That portion of the logic will effectively get enabled on the CXL link. So what happens is, once that happens, what actually gets activated? This is what gets activated. As we had mentioned earlier, the .io portion of the CXL is pretty much the same as PCIe because it's the same old configuration, DMA, reset, interrupt. None of that we are changing. We don't want to reinvent the wheel. It is pretty much the same. I would say 98%, 99% is the same. But there are a few extensions we've added that are specific to CXL on the .io. For example, there are some power management messages we have added as one example, right? Because we have caches on the other side. So if the system goes into some sleep state, we want to be able to, flush out the caches, etc. So, but there's some additional .io messages for synchronization that is added. So that is what is shown in this green. Even though this green is shown to be a big picture, big thing, it's a very small delta features we have added in the .io to enable this whole CXL protocol to work, right? And there are a few other things around address translation and others. I don't want to go into the details, that is its own topic. A few things like this were added in the .io. Okay, these are all delta changes. Now, this is where the big action is, right? The right side, the .mem and the .cache. So it has its own transaction layer because the .mem and the .cache, very different beasts, right? And people who are knowledgeable about cache coherency and all that know that cache coherency is its own beast, right? Messy protocol. It happens. There is no big payloads like you have on PCA. In PCA, you have 4 kilobytes of payloads, whereas in cache coherency, everything works on 64-byte cache line boundaries and things of that sort. So it's a very different protocol, and it has its own transaction layers with its own set of messages, right? Messy protocol requires a lot of, you will see the details of it, you will see later. It is its own thing, and there are separate virtual channels, separate queues with their own credits that are built, and the link layer is also separate for that. And then they get muxed down here. You see the dynamic mux here, because on the same link, you want to be able to send out a .io or a regular .cache transaction, right? Memory read, a snoop invalidate, a snoop current, a whole bunch of things are there, right? All of those are separate messages, and they go to your own link layer and they get dynamically muxed here. Okay, so at any given time, you can have a .io or a .io muxed out, and then they get sent out on the same logical file. Now you'll see here a static mux here. This is static because at negotiation time, if you are a PCI device or a CXL device, at that time the static mux get fixed. If you have PCIe, you send only the blue. If you are CXL, then you send the green. So it's static. Whereas this is dynamic mux because you dynamically have to send either a .cache or a .mem or a .io, right? So that's why this is a dynamic mux. And this whole thing is very, very extra care has been taken to make sure this thing is optimized for latency, right? Because people who are aware of the processor microarchitecture and processor performance know well that latency is very, very critical for processor performance. So every nanosecond of latency that you induce at the link matters. So this stack has been tuned to make sure that you get the lowest latency possible. And there are latency, recommended target latencies for this channel in the CXL specification. And that's what is mentioned in here. Okay. The other thing that I wanted to just quickly mention is the flits. So CXL introduced this concept of flit. PCIe didn't have the concept of flit. Now it is there in CXL 6.0, but in PCIe 6.0. In PCIe 5.0, there was no concept of a flit. CXL introduced that, and now PCIe 6.0 is adopting. It's basically a link layer concept where every time you send a message, there is a certain size of a message you send, right? So CXL 1.2 and 2.0 started on 68-byte flit, very optimized for .cache and .mem, right? And then now it is expanded to 256-byte flit that you will see later down. So all of the packets are all packed. So you have transaction layer packets, which is like a PCE concept, right? A packet, it could be up to 4K in size, but they're all encapsulated within these splits, which is a link layer concept. Okay. All right. So this probably is more interesting. At a high level, what are some of the usages that were intended for CXL? And this is expanding, but this gives you a good overview of where it started. So you can see on the left side, there is a type 1, type 2, and a type 3. Okay, so you will see this in the CXL specifications as well. A type 1 device or devices that support a .io and a .cache. See, all CXL devices must support CXL.io. It's a baseline, okay, because that's required for enumeration, discovery, configuration, etc. Right, the basic PCA stuff. On top of it, devices can support either .cache or .cache only, or they can support a .cache and the .memory, or they can just support .memory only. All these things are possible use cases. So for example, you could have a smart NIC that is only caching the processor memory, which it was not able to previously do. Okay, it was able to do only DMA, which was uncacheable semantics. So now, in those kinds of scenarios, the device only supports the .cache channel, it doesn't support the .memory, meaning there is no memory attached to this NIC that is cache coherent with the processor caches. That's what this really means, right? So those kinds of devices are called type 1 devices. Okay, and there is a type 2 device which is supporting all the 3 protocols. Okay, and these things are all negotiated at boot time, right, when the link comes up. So accelerators. So let's say an NVIDIA accelerator or an Intel accelerator, right? CPU Max accelerator, it wants to work in a very fine-grained collaborative manner with the CPU. So it wants to cache the process caches, so it will use a dot cache. Similarly, it has tons of memory locally, right? HBM memory, there's accelerators, a huge memory attached locally for very high performance. Now, you want to make some of that memory cache coherent with the processor because CPU wants to access that memory and caches in its own caches. How do you do that? Let's do the dot memory. Okay? So, so this is a GPU dense computation. So this is something that we expect the accelerators in the industry to go support. And then, this is another interesting one, which is memory buffer, meaning memory expansion. So typically, processor circuits have some amount of DRAM channels. They allow you a certain amount of memory capacity in the system. But what if you want to expand beyond what the CPU provides you? Hey, you can put memory buffers, memory expansion devices on CXL, and that memory itself, so you see here memory controller memory, and that itself is cache coherent with the processor caches. Okay, so for that use case, you have a type 3 device. So all of these three are supported in the CXL spec, and the usages are expanding, but largely they fall in these three buckets. How are we doing in time? Okay, feature evolution. Let's look at the feature evolution. So we get a sense for, how it's evolving and what kind of support and interest the spec is having right now, right? So when it started the 1.0 and the 1.1, it had 32 beta transfers. It tried to introduce the basic concepts of type 1, type 2 actually that we just saw, right? So we wanted to support all these three devices. And then it had, 68-byte flip format on CXL, very optimized for cache coherency, which, typically CPU lines are like 64 bytes in size, and so it was built around that with the 2 bytes for headers and 2 extra bytes for CRC, etc. Then CXL 2.0 still kept at the same speed, but you actually see that there are more use cases that were enabled in here. Sunita will talk about this memory pooling with MLDs. This has got to do with, when you have a data center with a lot of CPUs in a rack, and you want to enable pooled memory where that memory could be shared across these different server boxes, right? Dynamically shared, right? At one time, you could, depending on the workload running in one of the boxes, you can migrate the memory from one box to another. It's very, very important because this goes to the bottom, the total cost of ownership that the cloud service providers see, right? Because the cost of memory is increasing, right? It's the cost per bit, as I was mentioning earlier, is happening out. So it's very, very, very important feature to enable in the data center. So that's memory pooling, and then we also can support, persistent memory. That is memory that is non-volatile. So it doesn't have to be just the DRAM, which is volatile. You can support non-volatile memory as well. And there were some flows introduced for that. And then security. Security is everywhere, right? Anything and everything you touch in the industry, it has got to be secure. And there is a confidential computing consortium, in fact, in the industry, defining many of these things. We are adopting some of the basic tenets of confidential computing, and we started with integrity data encryption in CXL 2.0, and it's a never-ending topic. We are continuing to make CXL more and more robust as we move forward. And switching, yes. So when you start doing memory pooling, you also need switching capability. Those are introduced in 2.0. In 3.0, we introduced a significantly more set of features. Okay, almost every company has some capability or the other that they want to enable in CXL. So multi-level switching, direct access, I'll get to that later down. I don't want to spend too much time now. And we are making the packets more efficient. We are making the packets larger from 68 byte to 256 bytes. And we are enabling the memory pooling that we talked about earlier. Was limited to 16 processor nodes. Now with the GFAM devices and all that, we can go to 4K server nodes. that can actually share the memory on a common backend. And we are introducing something, we laid the foundation for something big that is going to, that is upcoming called Fabrics, okay? Fabrics is trying to not just pool, memory, but you can enable this concept of software-defined data centers, right? Because accelerators are not cheap, right? Data center builders, they want to buy certain number of accelerators, and then depending on the workload, they want to use that across n number of nodes, right, dynamically. That's true with almost any device that they purchase. So this is the concept of software-defined data center. That is what data center is one big compute node, and Fabric enables that. Okay, so we'll talk a little bit more about that later on. So these are some of the exciting things that are enabled, and we'll spend the next few slides going into a little bit more details on some of the important. We cannot cover everything here. Sunita will cover a few more things. Let's get into a high level on some of the key features that were enabled in 2.0 and 3.0, and then I'll end with what is upcoming in 3.0 as well. Okay, so memory pooling, I was talking earlier, right? So you have, so what is this feature trying to do? So you, in the data center, you can have host 1, host 2, host 3, right? N number of hosts, n number of, think of each of these things being a separate server box, right? In your rack in the data center. And you want to share memory, a common memory. Think of a memory, there is this big pool of memory in the backend that you want to share across all these hosts dynamically, okay? Why do you want to do that? The reason you want to do that is the total cost of ownership thing that I was mentioning earlier. Because the thing is so expensive, this goes to the bottom line of all the cloud service providers, right? In fact, of all the features we were, that CXL was originally intended to address, memory and memory-related expansion currently is like the biggest buzz, okay? Even though accelerators and heterogeneous computer are all important and they're upcoming, the most buzz right now is around memory, okay? And this falls right in that. Where in this particular picture, you can see that you can have n number of memory devices. Let's say each one is its own, has its own memory controller with a bunch of DRAM attached to it, let's say. You can dynamically allocate how much ever memory you want through a Fabric manager, okay, to any of these hosts. So depending on the workload that is running in each of these hosts, right, you can share the memory. If H1 has a whole bunch of very memory intensive workload running, you can see that it is got assigned a whole bunch more memory than the others, right? A lot of yellows here. Similarly, purple has a whole bunch of memory intensive workload running. So it's gotten, the others are, less memory intensive, so they have fewer memory assigned, right? Dynamically, you can do this. And so that, in totality, the memory that you put here would be lesser than if you individually were to size the memory. Otherwise, you would have attached to each of these hosts, right? Which is not practical beyond a certain limit. So the economy of scale doesn't work out. So that is the memory pooling that was allowed. It was done in a limited fashion, and in 3.0, we have taken the steps to enable it in a much more scalable way.
So when you have two hosts, will we be able to share the memory across two hosts? We have to partition.
Okay, so in 2.0 that was partitioned statically. In 3.0 we even allowed the share.
So I had following question, but I'll ask that.
Okay. So switching, as you can see, right, when you have a whole bunch of memory devices and you want to enable that to be dynamically switched across all the hosts, you need some expansion capability, right? You cannot put all these things directly attached to the one CPU, right? And allow the CPU to be the switching. That doesn't work. So we brought in this concept of CXL switch. It was not there originally in CXL 1.1. CXL 1.1 was originally intended to be a direct attach of the memory, just as an expansion for individual hosts. But with memory pooling, we want to enable CXL switch becomes a fundamental requirement for it. So that was also enabled in CXL 2.0. So 3.0, okay, so what more did it do? So in CXL 3.0, we allowed multiple levels of switching. That is one thing, right? So you see in the picture, there's only one level of switching that was allowed. 3.0, there were certain niche use cases where we wanted to allow more levels of CXL switching to get more expansion capability, and so that was enabled with multi-levels. We don't expect this to be the mainstream, mostly because the latency also gets impacted as you go and increase the number of levels of switches, right? But there are certain use cases where this actually helps, so we enabled it. But another important thing that we enabled in 3.0 is, so below a switch, because of various reasons, there was only one device that you can see here, right, that can have a dark cache capability. Meaning, even if, let's say in this particular picture, if all of this memory was replaced with the devices that are capable of caching, you could not enable it because of certain protocol limitations, right? Only one device per hierarchy was allowed to have the caching capability. We enabled that. We knew that there was a limitation, but because of various reasons, we went with it and enabled a much better solution. Up to 16 devices below a switching hierarchy can have caching capability. So these are some of the feature enhancements that we enabled in 3.0. Okay, so what are some of the other things? So this gets a little bit intense, so I'll do my best to explain. Otherwise, we can catch up during Sunita's presentation. So we enabled what is called direct peer-to-peer. Okay. What I mean by that is, in this particular picture, let's say, all these color codes, right, indicate that they all belong to the same host domain or the OS domain. Okay, so think of this logically as belonging to one physical box, whatever we normally used to thinking about, right? One box with CPU, with its own, assigned memory, device, cache, whatever, right? Memory. Now, that's a way to logically think about all these colors, right? So green colors are all belonging to the same host domain. So in 2.0, what happened is, let's say this device 1 and device 2 wants to talk to device 4 and device 6, right? They want to do direct peer-to-peer. So in this particular picture, this CXL switch, can allow the direct peer-to-peer, but in 2.0, because of various reasons, because of ordering reasons, we could not enable a direct peer-to-peer between device 1 and device 5. And even though the path existed, physically the switch can take a transaction coming from D1 and send it to D5. Okay, let's say a regular read or write transaction. But we couldn't enable it because it gets a little bit nuanced on why that is not possible. If you are interested, just catch me during the break and I'll draw a picture and do it for you. But we fixed that, but that's a limitation for performance, right? If you want to do that, what happens if D1 wants to talk to D5? You have to go to this D host, this H2 host, right? The transaction gets routed to the H2 and then it gets sent back to D4 and D5. It's an unnecessary scenic route you're taking, right? Latency, bandwidth are all issues. So we fixed that through what is called a couple of feature enhancements that we introduced in 3.0. One of it is UIO, unordered IO. So unordered IO is a class of IO that has no ordering requirements on the CXL fabric. Whereas you compare that to a regular read or write transaction that you have in PCIe, those all have strict ordering requirements through CXL switches or PCIe switches, right? The switch itself is required to maintain certain read versus write ordering, write versus write, all kinds of stuff. Good reason why it was done 20 years ago makes no sense today. Okay, so we fixed that with this unordered IO, and that allowed for this direct peer-to-peer to happen. Okay, or it allowed it removed one obstacle to get that happen. There is one more thing called back invalidate, where when D1 talks to D5, but let's say that line that D1 is trying to access is in the CPU cache. How would you do it? How do you take care of the coherence? So there's something called back invalidate that she will go through the details for. That back invalidate flow allows that to happen. So this all comes together and we have direct peer-to-peer solution that is enabled in 3.0. This is a significant enhancement. By the way, this UIO is not just a CXL feature, it is also a PCE feature. PCE is also enabling it now. and we are adopting that in here, and then and we are using it for certain interesting use cases in CXL.
Will D1 be allowed to put to D3 because it belongs to some other?
No, that is not allowed. That is not. This is an entirely different address domain. That is entirely different.
Suppose if it's a intellectual, if D1 has previously we have seen a slide where a particular device has memory with respect to different hosts. In that case,
So you just hold on to that for a minute. In the later slides, we're working on enhancements where D1 can talk to, let's say, D3 through what is called PBR switching. So accelerators can talk to each other and share data and all that through UIO. So in the baseline CXL 3.0, because these are different address domains, D1 and D3 cannot interact. And there are enhancements that we are working on where across domains also through a concept of GFAM, global address domain, we can make the thing also happen. Okay, just it's coming up further down in the slides. Okay. All right. What is this one? Oh, somebody asked this question earlier. I think it is you. So, okay, so how about, the case where there are different host domains and, can they have coherence between them? Okay, so we have enabled this, there is sharing between them, right? So you could have some memory that the two are using as mailboxes to talk to each other. That kind of limited coherence we are allowing in CXL 3.0. And this also a little bit overlaps with what you're asking, but a more general purpose solution will come a little later. Just hold on to it.
Very previous slide. Let's say D1 and D2 are talking to D5.
Okay.
It is possible, right?
Yes.
It is possible. So, and it is unordered.
Correct.
So, does program or like execution require or do not guarantee the ordering of invalidate of, let's say, some memory. So what I'm asking is, let's say D5 have a piece of data, D1 writes to it, D2 writes to it. Who gets there first? No one.
No, there is no ordering. The CXL switch itself has no ordering of UIO. Ordering is any producer consumer ordering requirement or maintained at the initiator. That is a funda around UIO. So D1 and D2 will make sure of that.
Hardware designer has to ensure that if one be.
Yeah, correct. So these two, D1, D2, and D5 are collaborating with each other. The source that issued knows inherently what ordering it wants, and it will do the right thing. So the onus gets put on the device rather than the fabric, right? Fabric has no idea what use cases are using it, right? So it cannot really do a good job, and that's what UI is trying to fix. Okay. Of fabric. So we are on the last section of this presentation, CXL fabric. So what is it that we are trying to do with CXL fabrics? So CXL fabric, a rough analogy to think of this is a network, right? Ethernet fabric. So we are now allowing, whole host of devices and processors, anybody, right, that has an Ethernet phone can talk to each other. We are roughly building that, but not exactly that, okay? But for data center level scale only, or rack level scale only, or I should say pod level scale. So we are trying to have a CXL based fabric that can connect up to 4K nodes, 4K, 4,000 nodes. So within a data center, you can think of racks, a number of racks, right? Making a big pod, okay? So all those nodes, whether it is a processor node, memory node, or some other IO node, should all be able to talk to each other and enable the different use cases, type 1, type 2, type 3 kind of use cases that we talked about earlier. So what is the protocol requirement that we need in CXL to enable that? That's what we are working on, and the fabric that we are working on is called as a CXL fabric. So it can have, it is, the key point to note here is, this is the star topology. You can have any kinds of topology here, right? Whereas PCIe, the traditional PCIe that we know of, is very tree-based, very hierarchical, right? there is a host, and then there is a switch, and there's a bunch of devices. There is a strict hierarchy. Here you can see pretty much everybody is a peer, right? That's what the Ethernet does, right? So we are trying to enable this at the pod level, and we are defining specific protocol enhancements to enable the switching to happen, right? And the switching, for example, you should be able, somebody was asking earlier, host, the purple host, if it wants to talk to the, these two hosts want to talk to each other through the CXL fabric, they can. But if two different hosts also want to talk to each other, purple and the yellow, you can do that through what is called as a PBR switching. Okay, specific concept where instead of coherency, there is no coherency semantics here, with some exclusion that I won't get into right now through type 3 memory device only. So you can talk in a very non-coherent manner. 3.0 is providing the plumbing for that between these different nodes. It's almost like, you do an RDMA today over Ethernet. There is no cache coherency there. Okay, and then you reach out to the remote node, and then you get the data, and then you work on it, right? Very similar semantics can be enabled with CXL fabric, and we are enabling the, enhancing the protocol to enable all that stuff through concept of PBR switching. So why is this important? I mean, we talked a little bit about memory pooling earlier, right? So we want to be able to enable memory pooling on a larger set of nodes. CXL 2.0 enabled only up to 16 devices to share the pool memory. Okay, that's a protocol limitation. Now we are allowing up to 4K. Host can enable, can share a common piece of memory. And we also want to enable this concept of software-defined data center, right? So you can have, so for example, this node, right, green node, today at any given moment, it is assigned to this green CPU, wherever that is, right? Green CPU, or this green endpoint is assigned to the green host node here. But as the workload in the data center changes, maybe you want to take this green accelerator here and convert it into a purple accelerator assigned to the purple host. You can do that. Okay, so this kind of dynamic binding and unbinding and all this, you should be able to do, and your protocol should be enabled that to happen. And that's what we are working on. So the software-defined data center, software-defined meaning it's dynamic. Software can define it at runtime. So all of these things we are enabling in CXL 3.0. The fundamentals, the protocol split level details we have enabled in 3.0, but there's a 3.1 spec that is upcoming soon that will, make the, complete the remaining set of requirements on switches and this GFAM memory that I will come to in a minute to make this a reality. Okay.
Is there a master host?
What's that?
Among the hosts, is there a master?
No, there is no master host here. So, so there is, it's not shown here. There is a concept of a fabric manager. Okay, so there is one entity in the data center that is able to configure all these things to be this green, blue, who belongs to green, that kind of stuff, right? Now, it could be one server box as a host, so that is also possible as a fabric manager. It's a nebulous term, but it's not your traditional host that is running your traditional workload, right? So there is a separate entity that configures all this. Correct. So that's it. And there has to be a trusted entity on the side that composes all this stuff. Okay, CXL 3.0. Okay, what is this GFAM device that I just talked about, right? The memory pooling we talked about earlier, MLD device, multiple logical device. I'd mentioned that it allows up to 16 hosts to share the memory on the back end. Now, with the global fabric attached memory, we are able to expand that up to 4K nodes. Okay, so the CXL fabric itself, works on a concept of node ID. So the CXL switches, right? They have to be what is called CXL fabric switches or PBR switches. Once they are enabled to support this fabric extensions, you can connect to what is called GFAM, right? Think of this as a memory pooled device, a much bigger memory pooled device, okay? Can go up to 4K hosts. You can have petaflops of or petabytes of memory attached to it, and you can dynamically through this fabric manager assign this to any number of hosts moving between one host to the other, right? Now that is all possible along with the non-volatile memory also, depending on your use case. So up to 4K device, 4K hosts can share this global fabric attached memory, and this works on the concept of global fabric address range. Okay, there is one huge flat address range that we have defined that, I shouldn't say flat. There is one fabric address range that each host maps to talk to this global fabric attached memory. Okay, and using that address range, it can then reach any of the fabric attached memory devices. So 4K, the best, much larger than the 16 that we enabled in CXL 2.0. But we need special switches for it because these work on the concept of global fabric address range, as I mentioned, and they also work on the concept of CXL fabric switching. So it's not address-based switching. So these switches, right, work on the concept of a node ID. They don't work on the concept of address ranges that the traditional switches work. Okay, so these are new switches that we need to build. But once you have it, you should be able to access a large set of memory at the back end. So what are some of the other use cases in CXL 3.0 fabric? One important use case is machine learning accelerator along with this memory, right? Think of a scenario where, let's say, there's a whole bunch of accelerators that are shown here. Okay, so there is a host, but there's also a whole bunch of accelerators, and they all have a whole, and they are all collaborating with each other on a large machine learning workload. And they are collaborating with each other, and they all share a common big pool of memory called this GFAM that we just talked about, right? So there is a CXL switch that is needed to enable it. And then the accelerators using the global fabric address range can access any of these GFAM memory. Okay, and the important thing to note is the GFAM memory is enabled through the .mem channel. So there is cache coherency from an individual. So this memory, right, you can carve out this memory and dedicatedly assign it to each of the accelerators, or you can also share and dedicate some portion as shared. Multiple hosts can use that to mailbox each other and talk to each other, right, to enable seamless communication. And you can have cache coherency on that particular range as well across hosts, which is a new thing, okay, that we didn't have in 2.0. So those use cases are enabled, and these things work on .mem channel.
So for the cache coherency, we need the CXL.
No, this is enabled on .mem. So the .mem has this backend validate channel that is enabled new in 3.0 that allows to take care of the cache coherency between the different hosts. So wait till the next sessions, she'll go through the process.
So it's like an extension to type 3 device, right?
Yes, that's an extension. I should say not type 3, it should say .mem channel, let's put it that way. Even type 2 devices can have this capability.
But these guys don't have flash.
Yeah, this one is type 3. This is type 3, but in general, the back invalidate extension applies to type 2 device. Anybody who has a memory. Okay. All right, so what is other use cases, HPC analytics? Similar thing as the previous slide, but in this case, let's say there's a large set of high performance compute workload that the hosts are running, and they all want to share memory, pooled memory, up to 4K nodes, and you can enable that through this GFAM, right? These are some of the interesting use cases. And the one that I kept talking about, the software-defined data center, is this one, right? So you can think of, so there's a whole bunch of NICs here. There is pooled memory, and there could be accelerators and other CPUs, right? So you can think of all of these things as being in separate racks, but then they could be physically on separate racks, but you can logically compose, any combination of these guys through this concept of the CXL fabric, right? So there you could say, oh, this accelerator yellow is combined. It's not shown here, I guess, nicely in the picture, but this accelerator could be working with another NIC, let's say this NIC in shaded yellow. All of these things could be in one host, one logical host, right? To enable this concept of fabric, software-defined data center, and the CXL switches could enable in this particular picture, you can see two levels of switching, which is what we think is typical in these kinds of use cases. A leaf switch that is connected to all these devices, and then there's a whole bunch of backend switches that switches between these leaf, right? So you can, anybody of these guys, leaf guys, nodes can be assigned logically to a given host to one. So this is a very, very interesting use case that is coming up brand new, and 3.1 will complete the picture for making this happen. Okay, so so summary is with 3.0 we have enhanced memory pooling, which is the GPAM device. Up to 4K nodes can share a common pooled memory, multiple levels of switching, and multiple fabric capabilities to enable the switching. And there is, we didn't talk about it, but we are also okay, this is, I guess it's not in here by mistake maybe. So there is a new symmetric coherency capabilities we are introducing in 3.1. By mistake, I put it in 3.0. So where devices can also issue .mem. It's called upstream .mem. I don't know if you are covering that or not, but there is some new symmetric coherency capabilities we're introducing and improved software. New usage models that we talked about, right? Peer-to-peer, sharing between hosts, fine-grained sharing of cache lines through that memory sharing feature, much higher bandwidth with 60 watts. So it's a lot of new things, right? And the 3.0 we believe will at least these things we don't expect all of these new features to get enabled right away. It will be staggered, but we do believe that CXL 3.0 will be seen in the market in the next 1 to 2 years. So a lot of new interesting capabilities. And much of what comes first and what comes later depends on what the value of the features we put in. And that's why we put a lot of time into analyzing these features, right? Which ones need to be prioritized to get into the spec. So we put a lot of time to vet these features with all the different data center vendors, right? Cloud service providers, to see what meaningful impacts are. In fact, like I was mentioning earlier, memory pooling is big now. Right? Memory related extensions is big right now, but we are seeing a lot more attraction around the CXL 3.0 as well. So that's kind of completes my overview session. How much time do we have for question and answer? How? I'm already over. We are kind enough not to interrupt. Okay, all right. Okay, so then why don't we do this? I don't want to take into our time. Let her finish, and then if you have any residual questions, we'll see towards the end, or we can do one-on-one after the meeting. Yes. Sorry, please let me. Let her on.
This will take approximately 40
We'll have a break in around 11:15, so please stay seated. We have a lot of material to cover. I would request you all to hold on to your questions till the end, just in the interest of time. For this, like a total about 100 or so slides to cover. Sunita is going to take us through 2 sessions, and we'll stop in the middle of the first session that she has around 11:15. So please stay seated until then.
How to set an again? Go to the Teams and then present.
It's already presented, but we should not see this one. We should see a full other conference room. We will check. There is one setting that there's no bypass set full screen. Is that black screen or white screen? Check this. This is full screen. This one. No, we should see it. We should see in the other conference rooms. This is what it presented. Unblock screen, white screen.
I will call driver.
Okay. So in the other room, we could be able to see the upcoming slide as well. So we wanted to plot it. Hello, Shika. Yeah, are you able to see the full slide? You're still seeing the next slide. Just a minute. Is Ashwin nearby? Yeah, now can you check it once? I set it to the full screen. Okay, good. Okay, thank you.
Yes.
Am I audible?
Yeah. You're audible here.
Am I audible? Last one. Okay, good. There. Good. Hello everyone. I'm Sunita. I'm from AMD. I'm a principal engineer at AMD. And thanks to Sridhar for a wonderful introduction to Computer Express Link. And for the next 2 hours, we'll go a little deeper. We'll look at the coherence protocol. What do we mean by .cache? We will look at what do we mean by .mem. And then we will go deeper into some of the popular use cases, especially the memory-based, memory pooling. And so in this session, I'll take you through CXL coherence. Is it okay? Okay. Okay. So in this particular session for next 45 minutes to 1 hour, we'll look at CXL coherence deep dive. And I would like to acknowledge from Blackship for this. I have taken the slides from the hot chips tutorial. A lot of interesting material over there. So to start off with, during this session, we will talk about, we'll give you a basic introduction to what is caching for those who are new to caching. And then we'll look at, we'll go a little deeper into CXL.cache flows with emphasis on understanding what is new in CXL3. And then we will look at CXL.mem flows with, again, an emphasis on what is new in CXL.3. And we will look at a couple of use cases which are pretty interesting. Now, let's get started on caching basics. So what do we mean by caching? So in a typical PCI Express-based accelerators, right, we have a host and we attach a PCI Express-based card to it. And you submit the workloads to the card does the functionality and you put the results back. So it works in a producer-consumer model. You don't see, you don't see this cache there. It's basically, you submit a workload, the device DMAs the data from the host memory onto the device. It works on the data. Once the results are available, it DMAs the results back to the host, and then your software can take over. But what if you have a use case where you have to reuse the same data, or think of scenarios where the data is changing and you're operating on it? That's where you need this sharing, and that's where the caching helps you. So to give you an example, let's look at Ethernet-based switching or routing, right? Your rules for Ethernet routing come from a central controller which is sitting on the host. For example, you take a OVS switch, open virtual switch or whatever. And your device basically is receiving Ethernet streams and it is doing the switching. It's looking at your routing tables, which are in the host memory. On a PCI-based device, you basically fetch your routes, you distribute, and then you figure out to which port the packet has to be forwarded. But with CXL, what you can do is you can get the routes into the device, cache it on the device in this cache. And if the rules change on the fly, the coherent protocol will make sure that what you have cached gets invalidated and you go and fetch it again. And that's the idea of fine-grained sharing. And that's where you need caching, and that's where your caching on the device helps you. And the CXL link basically makes it work. So the whole purpose of CXL protocol is to allow you to add coherent device accelerators. It could be accelerators, it could be memory. This particular session will focus on accelerators. So that's the concept of caching. It basically brings your data closer to the consumer. The consumer here is your accelerator. And you can do prefetching. Basically, if you know what kind of algorithm you are running, what kind of data sets you would need, you can always go and prefetch that data and put it in the cache. And then there is a concept of locality. You have spatial locality and temporal locality. Spatial basically means that if you access an address X in a cache line for the first 2 bytes, it's highly likely you're going to access additional bytes in the same cache line. And temporal locality basically means that you access the same data over and over. So in CPUs, we have caches. Everybody must have heard of L1, L2, L3 caches. Now, we extend the same concept onto devices. With CXL, your devices have caches, and they fall in the same hierarchy as your CPU caches. That's the idea of basically extending the, that's what CXL brings to us. It basically allows you to have a cache on device, which is in the same caching hierarchy as that of a CPU. And typically, we do expect the cache on device side to be of size around 1 MB or so, could be greater depending on the use cases. Now, okay, we know caching. We understood that, yeah, we can get data, we can store it locally, reuse it, coherency will be maintained. But how do we ensure that everybody sees the same data? Now, for that purpose, we have invalidates. So basically, there is a central entity, typically called a home agent, which is managing everything. So when we have a device which has cached a line, and say it has updated that line, it has written to that line, what does that mean? It means that the device has a line which has been modified. And if some other entity wants to access the same address, now that entity has to get it from the device, right? Or if we have a line and somebody else wants the line and wants to update that line, which means the line which we have cached should be invalidated. So the central entity, the home agent, will make sure that the line which is cached in the device will be invalidated. And then we have something called a global observation, or GO. And this is something which you will see in the flows in following slides, where we know that. So the GO basically tells us that the new data is visible. So your coherency has been resolved. That's what a GO means. And in CXL, we track the cache lines at 64-byte granularity. There are systems which do so at 128 bytes, but we're going to be focused on 64 bytes, and that's what the protocol is about. And on a coherent link, all the addresses are physical addresses. We are not dealing with virtual addresses on the coherent link. You can have accelerators. Your host or your application can program the accelerator with a virtual address using the shared virtual address paradigm, or the SVA or the SVM. But any transaction which is issued on CXL link should use physical addresses, and it uses the same PCI address translation services. And these address translation services are exercised through CXL.io. Now, a quick run through the coherence protocol. So we basically are following the MESI protocol for CXL. And what we mean by MESI is M stands for modified, And this basically means that the data is dirty. It is only in one cache. It can be read and written to. And the data in the memory is not up to date because the data which belongs in that cache is dirty, has been modified. The next state is exclusive, which means the data is again only in one cache. It's not dirty. And the data is same as what is in the memory. The third state is shared, which means data is available in multiple caches. The copy in the memory is the same. And invalid basically means it's not in any of the caches. Okay, so CXL protocol follows MESI. There are variations of MESI where additional states have been introduced, but for the purpose of CXL, we will only stick to MESI protocol. And we track it at a cache line granularity. So we support 52-bit addressing in CXL. And so we use, for 64-byte cache lines, we use address bit 51 down to 6. And as I mentioned, the central entity which is responsible for resolving coherency is the home agent. And it basically tracks the ownership of all the lines across various caches. Because there has to be some central agent which needs to know who has what data. Otherwise, the whole system goes for a toss. And a snoop is the term which we use for the home to check the state. So basically, what we say is, let's say a device has taken a line, it has cached it on its cache, and it's in the shared state, which means it's just reading it. The data is same as in the memory. But there is another entity which wants to access that line with an intention to modify it, which basically means a snoop has to be sent down to the device to invalidate that line in the cache. Now, that was a quick run through on caching. What does caching mean? And let's go a little deeper into the CXL.cache protocol. Okay, so the cache protocol defines a set of 15 reads and writes from device to the host memory. Now, these are specifically the cases where the request initiator is the device. Okay, and so we have reads. There are variants like read shared, read current, read any, and read own. We have read zeros, which basically mean this is just a read. It only returns a go. You don't get data for this. There is zero data. That's what that zero means there. And then we have writes, different categories of writes. And then we have streaming writes. And the global coherence is managed with the host. So the thing to remember is CXL is an asymmetric protocol. You have the home agent only on the host. And that keeps basically the design simpler. And then as part of device scaling in CXL 3.0, we enabled addition of up to 16 cache devices below each port. Till CXL 2.0, it was just one accelerator or a one caching device, which was allowed to be connected per root. So looking at this, so we basically have 3 channels in each direction. And the terminology is H to D basically means host to device. And D to H means device to host. That's the naming. And you can see here a D to H request, which means a request channel coming from device to the host. There is a D to H response, which is a response channel from device to host, and a D to H data, which is a data channel from device to host. Now, a D to H request is one where the device issues a request, and the response from the host comes back on the H to D response channel. If data is needed, it comes back on the H to D data channel. The host can issue snoops on the H to D request channel. The snoops come downstream into the device, and the device issues the snoop responses on the D to H response. And if there is a data needed to be provided back, it does so on the D to H data channel. And the ordering requirement is simple. The H to D requests, the snoops should push the prior H to D responses to the same address. That's the only ordering requirement. We are going to look through some of the flows of the CXL.cache. This is the legend which we are going to follow. On the x-axis, we will see the agents, and on the y-axis, we have the time flow. And we have CXL device, we have pure cache, we have home, and we have the memory controller. The boxes with the letters are basically going to indicate the cache state, represented by MESI. Just now, next slide, we will just try to identify these agents in a hierarchy. So here is a diagram where this is the CXL device, which we are talking about. When you see the agent in the flow diagrams, this is the CXL device we are focusing on. And when we talk about pure caches in the diagram, it could be the CPU cache. It could be a cache on a pure CPU, a CXL device. It could be a pure cache on a pure socket. So these are all the pure caches which are possible. And then when we say memory controller, memory could be the native DDR on the host. It could be a CXL attached memory, which are the two boxes here. And then it could be memory on the pure device. So this is how we have the association, or it could be a CXL.mem on a pure device. This is what we saw here. Getting into the flows, so this is the first very simple, the simplest one, the read flow. So in this, the device basically it doesn't have a line. That's what the line indicates, and it wants to read that line. And the intention is to read it only. The idea is not for the device to modify. So we issue a read shared. So we get the line in shared state. So remember that shared basically means you have a copy of the line, the data is also the same as in memory. So we issue a read share. Now for the same line, it is in a pure cache in exclusive state. What does that mean? It means that the pure cache has the line. In exclusive state, data is same as in the memory. Now this read share goes from the CXL device to the home agent on the host. The host, basically the home agent knows it's tracking, right? It's a central entity which is tracking everything. It knows that, okay, this pure cache has this line in E state. It issues a snoop to it. And then it changes because see, we are requesting, the device is requested for the line in shared state. So we don't have to invalidate that line. The intention is only to read or get it in the shared state. So it just issues a snoop to change the state from exclusive to shared on the pure cache. And the pure cache response is saying, I have it in S state now. I had a hit in S or E, and I have it now in S. The response comes back. In parallel, the home agent can also fetch that line from the controller. So once the coherence is resolved here, it responds back to the device with a go S. S basically indicates the state. This is the global observation which says coherence is resolved. You have the line in S state followed by data. This order could be anything. One could see data first, followed by go. And then at the device, you have the line in shared state. So this is a simple read flow. Now coming to writes. So writes are slightly more complicated. They basically have three phases. First is an ownership phase where you want to write and you want to cache that line. So here we request for a line using read own. So read own basically says that the device wants the ownership of the line. The intention is to modify the line. So we are basically requesting for an exclusive ownership of the line. So there is the same line exists in a pure cache in shared state. So the request, the read own from the device goes to the home. The home agent knows that there's a pure cache having that line in shared state. Here it issues a snoop invalid. Basically, it's invalidating that line in the pure cache. That snoop INV tells the pure cache to invalidate that line. And when it responds, it's basically telling, I had a hit in S and E and I'm responding with I. So now my final state is I. The coherence is resolved here. Meanwhile, the home agent fetches the data from the controller and it's ready with the data. And then we provide go E, which is go with exclusive ownership state back to the device along with data. So now the device cache has this line in exclusive state. This is called acquiring the ownership. The second phase is where once we have the line in the cache on the device side, we can write to it. We can write to it multiple times. First time we write, we basically change the state from E to M. M basically indicates modify. And we can write or read it multiple times on the device side. There are no CXL transactions at this end because we already have the line cached with us. The last bit, where we want to write the line back into memory. What we do there, we issue a dirty error. Now dirty because the line is dirty with us. It tells the host that there is going to be data which is going to come your way. What does the host do? The home agent basically, now once it sees dirty event, it keeps your buffers ready. It needs to cache, it needs to be ready to sync in 64 bytes of data. So it makes sure it has the space. It issues a go write full. It's a single command, a go saying that it's all resolved, I'm ready, and write full is basically send the data, I have the required buffer. The device then sends the data and it changes its state from M to I. The data, when it is received by the home, can choose to write it to the memory controller or it can choose to put it in the last level cache that's specific to the host implementations. So that's called the cache deletion. Now, you see for this simple write, we have so many transactions on the link. We have another variant of writes which are called streaming writes, wherein we don't take the ownership of the line beforehand. We can issue the writes directly. Now, this looks like, oh, very few transactions, but then let's see what's the catch here. So we do a direct write to the host. So we have the line in I, there is some peer cache which has the line in S, and we are issuing from the device a streaming write, which is a ITO and write. And because it's a write, the home agent will do the same thing. It will invalidate the copies in the peer caches. And then once that is resolved, it will issue a go write full. And then the device can send the data back to the home. Now, right, this has fewer transactions on the link, but then if you wanted to do ordered writes, if you wanted to do multiple writes, you basically have to wait till here, till the go is received to issue additional writes. That's where you lose out on bandwidth in the streaming flows. If you have use cases where you want to update the same data multiple times, you are better off using the previous version of writes because you have the data in your cache, you can do multiple updates to the same data. But if your requirement is to basically do things like this, where you have ordered writes, but you want to write once in a while, you don't want to write frequently, you are better off doing this because of lesser transactions.
Devices that make streaming writes the same.
So that is up to the home agent to resolve. For the home agent, whichever one sees first, right, it will resolve it at that. Now that was about the CXL cache protocol. And now let's look at the MEM protocol. MEM protocol is again simple reads and writes from host to memory. Now one thing to remember is CXL.cache, the originator of the request is device. And the originator of snoops is the host. Whereas CXL.mem protocol, the originator of the request is the host. The host is the one which is accessing the memory, which is sitting on the device. And the kind of memory you connect on the device, the host is totally agnostic to it. Host doesn't care what kind of memory you connect. It's basically very similar to a natively attached DDR on the host. The memory technology on the device could be anything, HDR, HBM, DDR, or persistent memory. Now, we also include 2 bits of metastates for cache line, and for type 3 devices, where they are used only for memory expansion purposes, the definition of those 2 metabits is host dependent. The spec does not define the interpretation of metabits for a type 3 device. The spec defines the interpretation of metabits for type 2 devices, where you have accelerators as well as memory on the device. And now, when we have memory on the device, you're going to see these kind of terminologies. So what we call the first thing is post-managed coherence, or HDMH. HDMH is basically, think of it as a purely type 3 device. And you don't have pattern validations. It's like just a memory expander from a host perspective. Next is HDMD, is typically a type 2 device, a device managed coherence. And here there are different ways the coherency can be managed. And then we have device managed coherence with back invalidation. This is called HDMDB. This is something which has been added newly in CXL3, and the B basically indicates the back invalidation. That's the new feature in CXL. Coming to the nomenclature of the channels here. So we have 3 channels in each direction. M to S basically represents master to subordinate, and S to M is subordinate to master. So when the host issues a request to the device attached memory, it does so on the M to S request channel, which is the reads. And for the writes, it uses the request with data. And the responses from the device go back on the S to M no data response, which is for the writes. And for reads, it goes on data response, this one, the S to M DRS. In CXL3, we have added BI response on M to S and a BI snoop. So CXL3, the backend validation basically gives the ability to the device to issue backend validation snoop requests to the host. And we'll see a little more about these things as we dig deeper. And in terms of ordering, the request channel should be ordered on HDMD. What do we mean by that? If we have requests to the same address, they should be ordered. And the non-data response channel should be ordered in HDMD. This is because we have added BI conflict flows, and we require that to be ordered. Now, so this is a difference. We have a HDMH device, which is a typical type 3 memory expander, and that's how it's a directly attached memory. It's a memory expansion from a host perspective. Whereas when we have HDMD or HDMDB, there is additional caching agent for coherency resolution, which comes into place. We have a device, we have an accelerator with device attached memory. That's the distinction. That's the way to look at it between type 3 and type 2, or it could even be type 1. Cache basically the CXL mem write flow. So in this, we have the host, and the dotted box is basically the device, which has the controller and the memory media. And the host can issue a write with a new meta value. The write can come with a new meta value along with the data which it wants to write to the cache line. And then the responsibilities of the device to translate that CXL mem write to the format which media understands. And then it does a memory write with ECC and meta bits. Once the write is committed, it can send the completion back to the host. In this particular diagram, we see the completion being sent to the host after we receive the completion from the memory media. It's not required to be this way. The completion to the host can be returned as soon as the device can guarantee that the write is committed to the memory media. And this is a case where the host can cache the lines from the device. Now, the host can read or write, and it can cache these lines. And this is an example for a memory read. The host can issue a memory read. We are not interested in updating the meta fields. So we issue the read goes to the device, and we get the data from the memory and send it back. Now, there are 2 different ways to update meta values. And one is the host reads and updates meta value only. So there is a memory semantic called mem-inv on the M to S request channel, wherein it can be used to update just the meta values. And then the response is only completions without data. And what happens here basically is you receive the mem-inv, you issue the read to the memory media because we have to provide the existing meta value back to the host. And then the onus is on the device to update the meta value thereafter. The other flow to update the meta fields is basically to do it with reads. The host can issue a read with the new meta value. In the read, it's the same flow on the device side, but the difference being you get the data back here in response, and here you don't get the data back. So depending on what the host wishes to do, it can use either of these flows. So we have looked at all the flows on cache and MEM, and now we will digress from here between HDMD and HDMDB. HDMDB is basically a new concept with CXL3. What are the common aspects between what we had before? So we had, so this memory, the memory attached on the device is device coherent, where both the host and the device can cache this memory. And we have the meta fields, which indicate the host cache state. Now, it's very important to remember that we're not talking about a type 3 device here where the meta fields are specific to the way the host defines them. We're talking about a type 2 case where the meta fields are defined in the specification. And the meta fields in a type 2 flow will basically indicate the state in which the host wants the data. So any, shared, and invalid. And then we also have Snoop type fields on the M2S channels, which will indicate the device cache. What should be done if the line is a bit in the device cache? So you have a device attached to memory. It can not only cache the host addresses, but it can also cache the device memory addresses. And then we have what is called a device coherence engine, which resolves the conflict between the host and device when they are accessing the HDMD star D or DB. You can think of the core engine as a pseudo-home agent, a very lightweight, but a pseudo-home agent. We'll take a break here, and then we will 10 minutes break, and I think it's 11:15 now, 11:25 break. Thank you.
Let's assemble back in about 10 minutes. It's quite a bit of material to cover. So let's be back at 11:25.
you can, on the back end, you can actually CXL and then assign anybody to this. Logically, at least that's nirvana. Let's see how where we go. We're still crawling.
Switches are also connected.
That is correct. That's correct. The NICs could be, a pool of NICs could be.
There's a sign-up sheet here. Please make sure you signed up before you leave the tutorial. We'll just pass this around.
Display the
We have
presentation.
about 90 odd folks here in this room and
Sharing
more than 60 in the others. So good attendance. Thank you all.
Yeah.
And
This is the
hopefully
one.
can settle in very quickly so that Sunita can continue on from where she stopped. One request, please walk through the sites when the session is ongoing so that Sunita is not disturbed.
Let's continue from where we have left off. Talking specifically about HDMD. So it's okay. Is that okay now?
No.
It's okay. Is it okay? Let's talk about HDMD specifically. When we talk about HDMD, we are talking about the flows defined in CXL 2.0. So here we basically have a device with a device cache, accelerator, and a device attachment. The way these flows work is there is a the device needs to access the device attachment. Now, you may wonder, it's a direct access, I can directly go and access. But it is possible that the host had access to this line from the M2S channel, and it may be caching the line. So you cannot go and access this directly, even though it is located on the same device. What you need to do for that, you need to go to the host, issue a D2H request, and the home agent would figure out that the address belongs to the device attachment. And then it resolves the coherence and it issues a forward flow, what we call as a forward flow. It issues a forward flow on N to S channel. Okay, so this is a long path, obviously. And this, what we do, what we basically define in the specification is you can implement a bias table on the device to track this. Now, what do we mean by that? Now, we call it a bias table, and what we are trying to say here is, so you see the blue line. The blue line is basically the host accessing the device attachment. The host always has a direct path to the device attachment memory, independent of the bias state it is in. And in case of device trying to access device attached memory, it has to flip the BIOS in case the line is cached with the host. Okay, so it goes, flips the BIOS in this, then it accesses the line. Now we call, there are cases where the line is with the host. The second diagram, wherein the device goes to the host issues a forward flow, it comes back, and then the device accesses the line. This is called a host bias mode, wherein we have to go to the host to resolve the coherency for a line, which is in the device attachment. And the above one is a device bias mode, wherein the device, once the bias is resolved, and we know that host is not caching the line, it can actually directly access the line on the device attachment. Okay, So for this, one can implement tracking table on the device. You can track. The requirement from the specification for CXL 2.0 is you have to track the entire device attachment. You cannot say I will track only a certain set of it because there are some semantics which can cause deadlocks in such scenarios in 2.0 spec. So you have to track the entire device attached memory, and that can become painful actually. So we'll look at that problem in future slides. We'll just try to understand how these flows work when in particular bias modes. So this is example. This is an example for a read in post bias mode. What does the bias being in post mode imply? It implies that the CPU or host has the line, and I cannot directly access the line from my device attached memory. So the device basically issues a read home, and the device coherency engine, it identifies that it is in a host bias mode, issues a request on the D2H channel to the host. The host will resolve the coherency based on if the line is available in clear caches or not, and then it sends a memory read forward. Now, remember that this is a forward flow which comes back on M2S channel. We are not responding to this request which came on D2H on H2D. This is an important difference. If we are accessing host address space, then we send the response for read-ons back on H2D response channel, the flows which we saw before the break. Whereas if we are accessing this address X is in a device attached memory, you will end up seeing the forward flows. So basically you get the forward flow response and then you handle the device will handle it. So it will read the data from the device attached memory and give it to the device mesh. This is an important difference to make. Now the same read if the line was in device bias mode. Once the line is in device bias mode, we know that the host does not have a copy of this line, and the accelerator or the device can directly go and access the line from the device attachment. Similarly, cache evictions. Once we are doing dirty evict, what does dirty evict mean? Dirty evict means that we have the line in modified state, which in itself guarantees that there is no other cache where this line is present. So you could directly go and write this data into the device attachment. Now, similarly for streaming rights, you have the streaming rights wherein we don't have to take the ownership before. The line is in post bias mode. You will go ahead and issue the request on the CXL link. Again, this weekly ordered write goes on D2H, and you see the forward response coming back on M2S. Likewise, in device bias, you will not see any transactions on the CXL link. This can be handled locally on the device itself. Now, we talked about the need to track the entire device attached memory, basically having the bias data. Now, why does it cause deadlocks? See, the forward flow basically what it means is you issue a request on D2H channel, but you are getting a response back on M2S channel. There are totally two different channels, and if one is backed up, you end up in a deadlock. What we have done to solve this in CXL3. So in CXL3, we have introduced two new channels called S to M VI snoop. VI is back invalidate. We have a back invalidation snoop, and we have a M2S VI response, which is the back invalidate response. And these are introduced primarily for the purpose of solving those deadlocks. Now, how does this work? So you see in this flow, we have the host. So here, what is back invalid? So before we get there, the VI channels enable a device to implement a snoop filter. If we were to do that without the VI channels, we would have to track the entire device attached memory. The memory can run into gigabytes, and you have to start tracking all the cache lines. That is not realistic for device implementations. But with the VI channels, you can implement an efficient snoop filter on the device to track whether a particular line is with the host or with any clear cache. Now, What happens here is the deco just has a Snoop filter. So we have a scenario here where we have a line at address Y with the beer cache in modified state. And the host is issuing a mem read to address X. Now this X belongs to device attached memory. And the read comes in. And what we see is now when the host is issuing the request, it says that invalidate your caches, invalidate the device caches. That's what that Snoop type field or the Snoop invalidator is telling, which means the host intends to acquire the ownership of the line, right? Which means that you start tracking it in your Snoop filter. You need to know that the host is going to cache the line. Now, this is a scenario where the Snoop filter for that particular address space is getting filled up. You need to victimize a line at address Y in order to accommodate the tracking for address X. Now, while this comes in, you realize that you have to victimize line Y. How do you do that? With BI Snoop, you can actually send a BI Snoop Y, which is basically we are telling invalidate the line Y. Because the Snoop filter is already tracked that some peer cache has this line. So we send the BI Snoop INY, which when received by the home agent, will go and invalidate the line in the peer cache. And what happens as part of that invalidation? Because this line is in modified state, it will be written back. And this Y also belongs to the device memory. So there is a memory write, which happens on M2S channel. The data for Y is written back, and this transaction is completed. Only when the completion for this memory write Y is received, does the host respond with the BI respan, which basically tells that this has been victimized. So we wanted to do an invalidation on address Y. We wrote the line back into the device attached memory, and then we send the BI respan. And here, then we know that the line has been returned. The Snoop filter need not track that line. It has been victimized successfully. And then the Snoop filter can start tracking X and provide the response, the comp E response along with the data, which it had read before. So this is what the BI Snoop channel enables us to do. A very high performance Snoop filter, which can be implemented on the device. Now, we also introduced the concept of block accesses with CXL3, specifically on the BI Snoop channel. Now, there could be cases based on the use cases that you may not want to do BI Snoop for every 64 bytes. Based on your use cases, you know that you want to access more data than just 64 bytes. So you can actually do a block BI Snoop. You can do up to 2 or 4 categories. And the way it works is you issue a BI Snoop IND block-wise. So there is a specific opcode which is defined for the M2S BI Snoop channels. You can indicate that, and then the home agent will take care of all those 4 cache line or 2 cache line addresses individually, treating as if it has received 4 BI Snoop channels for all those 4 addresses. And then it can, once it resolves, and it sends a BI Snoop response I block response, which basically says this block request has been resolved. And then the device can locally read all those lines and do whatever modification or caching needs on it. Now, we look at what are the use models which HDMD enables. Now, Caesar did talk about direct peer-to-peer. And we'll just take a look at in a little more detail. So in the previous generations, which is before CXL3, if we wanted, so let's look at this topology. We have a device which has memory, and that memory is HDMD, which means that the device D1 is capable of, it has a backend validation channel, it supports BI. And then we have device 3, which is just a CXL accelerator. It could be CXL or it could be a D2, which is a PCI-based accelerator. Now, typically, if the D3 or D2 had to access D1, the memory or D1, they would have gone to host H1. The host would have resolved code and C, fetch the line from D1 and send the response back. So what what would that do is that would basically make this link busy. And what we are doing here by enabling peer-to-peer is you can directly access D1, D3 or D2, you can directly access D1 without going to the host. And how are we doing that with VI Snoop? Now, let's say the D3 issues a request to D1. Based on the Snoop filter we have in D1, we know that that line is cached with H1. Using the VI Snoop channels, we can actually go ahead and invalidate that line in post, forcing it to write the line back in case it is modified, and then we can respond the data back to D. If the line is not cached with the host, it's a fast path, the D1 can directly respond back to the requester. So these are the set of use cases which are enabled by VI Snoop channels. And in CXL 2.0, we introduced the concept of memory pooling. What do we mean by memory pooling? See, there are use cases where you can connect dedicated required memory to your processors for those particular use cases. And as we see, there is the whole data explosion with AI and ML use cases. You can't keep adding memory to your CPUs. That just doesn't work. So what you want to do is you want to use your memory efficiently. So you can basically have a pool of memory assigned to the required host on a need basis, based on the use cases. So what is important to understand that in pooled memory, the memory is dedicated to a particular host or the OS. It's not shared. It's assigned to that. Whereas in CXL3, with the inclusion of backend validation, we can have memory which is shared. And so we can have memory which is shared across hosts, and then the backend validation will take care of resolving the codes. That's what is enabled in the shared memory concept with CXL. In summary, the CXL protocols are evolving. We have seen a big jump in CXL3 enabled use cases from CXL 2.0. We have device scaling, we have backend validation has opened up a lot of use cases. And what we would like, and we will see more enhancements in the future. Yeah, I just wanted to say to everybody to get involved with the CXL consortium and help us enhance it further. And we do this now or continue? Okay, let's finish off the second part of the session, and then we can take all the questions at the end. So the next session is about memory. We know that CXL attached memory, that's one of the most popular use cases. Even now, if you see everybody's talking about memory expansion with CXL, that's the thing which is picking up right now. You do not see as many use cases or deployments with CXL.cache today, but CXL.mem has definitely picked up. And in this session, I'll just talk about what is making it so popular and what are the challenges in actually using CXL memory and what help is needed from the ecosystem. I would like to acknowledge Mahesh Wagh from AMD and Prakash Chauhan from Meta for the content on these slides presented as part of our chips. The agenda for the next, we'll try to keep it short. We'll look at memory trends and challenges. We'll look at what is CXL doing with memory, how is CXL attached memory helpful, and we will look at what are the challenges at the end of it. So in this graph, if you see, we see that the CPU core counts are increasing, but then we don't see the increase in the memory bandwidth per core. Memory has basically more or less flattened out, or we don't see the advancement happening as fast as we are seeing on the CPU side of things. Additionally, the cost per bit is also flat on memory. So this gap between the CPU core counts and memory is increasing. And what we have today is because of the use cases like AI or ML, which need a lot of memory, this is becoming especially challenging. So at the system level, what can one do? In today's world, without CXL, you could add extra DDR to the CPU. That's one solution of solving your workload problems. but that would make your CPU sockets huge. It is a cost penalty for you. And then you also need, if you add additional DDR DIMMs, you have to have your extra layers in the PCB, which is again having a cost implication. And you can also go for a DDR with higher data rates. Again, when you go to higher data rates, you have to be mindful of signal integrity on the PCB design. Again, at cost. And with the data rates increasing, we are now moving towards 1 DIMM per channel. We are not going to have 2 DIMMs per channel as is common today. We are going towards 1 DIMM per channel, which means you will get extra bandwidth, extra speed on the DDR, but you are going to take a bit of capacity. Now, overall, the memory density and the bandwidth is not keeping up with the increasing CPU core count for the kind of use cases we are seeing. What is now? CXL gives you a media agnostic interface. What do we mean by that? It allows you to attach memory to a CPU. That memory could be anything, could be DDR, LPDDR, or persistent memory. It allows you to add it to the CPU, and it allows you to augment the whole system memory. The CXL attached memory is viewed by the system just like its own native DDR with the same load store semantics. And you can have media with different characteristics. So you can basically connect heterogeneous memory, and this goes into a slot with differential signaling. So you don't have the challenges which we saw in the previous slide. And that is why we call it tiers of happiness. We can introduce intermediate tiers with CXL attached memory, wherein the latency would be along the order of a cross-socket memory, so from a socket to socket memory access. And what it allows us is to build a memory hierarchy this way. One could have a system where you have all the DRAMs for performance reasons, but with CXL, you can augment your system with a CXL attached memory, and the memories could be of different kinds. And you can enable a slower memory tier, which is totally isolated from your main memory tier, and you can enable use cases. There are use cases which can take advantage of remote attached memory. So here is one example of how you can have a flexible system with CXL. Could have a lower count CPU with these DIMMs, but if this expanded from a lower core count to a higher core count CPU, we don't have provision to increase the DDR here. You can do so by using a CXL attached memory. And that's the flexibility which CXL provides. And in addition, CXL also gives you cost saving advantages. So in this particular example, let's say we have a use case which needs 2 GB per core. For 80 cores, you end up needing 160 GB of memory. You could go with a solution of 8 DIMMs, 16 GB each, but it does not serve your requirement. You could think of going for 32 GB DIMMs, but you exceed your requirement, which means you end up paying more for the memory, which you're never going to use. In such cases, you can actually look at a CXL-based solution. You can realize it. Now, a CXL attached memory uses CXL type 3 force using the CXL.min semantics, which we saw in the last session. So again, just a quick recap. We have writes, we have reads, and we have metadata update to the invalidated bits. And what does the CXL attached memory give you? It basically allows the host to cache the HDM lines, uses a load store semantics. Now, let's look at the evolution of CXL attached memory. Here, this is where we are today. This is the first generation deployment of CXL systems, and where we expect most of the systems to directly attach to the system for memory expansion. It's primarily going to be used for capacity expansion. It's a slower tier which you can add in, and it is going to use CXL version 1.1 mechanisms. Moving forward, we are going to see an increasing use of full memory with CXL, primarily on CXL 2.0 specifications. And here is where we can have flexible allocations. Like I said, you can pull your memory and share that or dedicate it to the host which needs it. Moving forward with CXL 3.0, we are going to see deployments for shared memory, wherein you can have hosts sharing memory because of the PI channels which are in place. And moving forward, like Sridhar mentioned in the morning earlier, we are going to have fabric, which is just a huge scale out, giving you a large scale memory disaggregation. Now, let's talk a little about cooling. We have been hearing about cooling, but what is it actually? Now, before we go into cooling, let's try to understand how does a CXL type 3 device work. Here is what we are showing, a single logical device. We have a device and we have a memory attached to it. Has a CXL link. Now, the way a CXL attached memory works is you connect this memory. Now, how does your system know how much memory is attached? What am I to do with it? So there are capabilities which are defined in the configuration space, which can advertise what is the size of memory, what is the kind of memory, what are the performance characteristics of the memory, and so on. So all those details are advertised, and the host can actually read through once it does the enumeration and understand what is the device, what is the capacity, and then the host assigns it an address space in its memory map. And when you attach a memory on the device, the address of the memory is private to the device. I mean, when you connect something on your device, you know the logic on the device knows how to access that memory. What is the base address of that memory? And when the host assigns a physical address to this memory, that address lies with the host physical address to him, right? The host does not know what is the address in the device space. Host only knows its own address in the physical range. So we have HTM decoders, which are again registers in the configuration space, wherein the host can program the host physical address. And the onus is on the device to do a host physical address to device physical address translation. As the accesses come in from the host, the responsibilities on the device to do a HPA to DPA translation.
So these devices are hot connected, right?
In 2.0, yes, they are not in 1.1.
And how will the physical address mapping change if
We'll come to that in the next slides. Okay, so this is the whole concept of a single logical device. Here we have a multi-ported full memory device. It's again, each of them is a single logical device, and you can see that there are multiple CXL ports. So it's like a multi-headed CXL device, each of them being a SLE. And you can have memory, you can attach to different hosts via a switch, and then you can dedicate the memory to each of them. A multi-logical pooled memory device. So this is a concept which is introduced in CXL 2.4. Here you notice that you can have up to 16 logical devices, but with a single CXL link, as against this one, where we have individual CXL links. So here we have a single CXL link, but we can have up to 16 logical devices. We have one logical device which is reserved for management, which is called for configuration. It's called the FM on LD. FM stands for Fabric Manager. And what happens here is there is in the M2S request, there is additional field, 64 field, which identifies a logical device ID. So when you bind, so the FM is responsible for binding these to the hosts. When it binds a particular LD to a particular host, when the host issues a transaction, you get the LD ID fields in the transaction. And based on that, the device directs that transaction to this LD, wherein it does the decoding. Okay. We looked at Fabric Manager. We just heard about Fabric Manager. Fabric Manager is an abstract concept. It's just a control entity which manages your resources. Now, it could be an external VMC, it could be a host, or it could be a firmware on the switch as well. And what it does, and this is where it helps the dynamic changes which are happening on the system. It can do binding and unbinding of the logical devices. And how it does that? Let's look at an example. So here we have a single logical device. And this is an example which will follow the PCIe hot plug semantics. So here we have the yellow memories and the blue memories, and H2, which is the blue one, says that I don't need D4. So it communicates with the fabric manager. Now this link of how the H2 communicates with fabric manager is not defined in CXL specification. It could be anything. There are a lot of industry standards around for that. You could use SM bus, you could use Ethernet or whatever. So the fabric manager informs the switch using the fabric manager APIs. So these fabric manager APIs are what are defined in the CXL spec. They are following the MCTP protocol. So there are APIs which are defined. So the fabric manager is informed, and then the fabric manager informs the switch port to basically remove D4 instance from H2. This follows the normal PCI mod plus scenarios. There is nothing CXL specific. Again, when we have, this is the third figure is showing a case where we want to augment the memory of H1 by D4 which was released. Same scenario happens, PCI based hot plug, hot memory attached, wherein the switch tells H1 that there is a presence detected, and then it goes and adds in additional memory. How the memory is added, how the address is assigned to it, there are mechanisms on the OS for memory hot plug which can take care of this. Now, coming to the same scenario with MLDs. What happens with MLDs? We don't have anything related to PCI hot plug here. The owners of hot add or delete of memory location lies with the device. What has CXL spec done for this? In the CXL spec, we define something called coherent device attributes table. It's called a CDAT table. The CDAT table tells us what is the memory, what is the characteristics of that memory. Any change to the CDAT table causes an interrupt to the host, and the host needs to figure out, then the host understands that there have been changes on the device side. It goes and looks at the changes and then adapts itself to it. Now, here we are basically showing the case where H2 wants to release up the memory on D2. The FM is informed, and the fabric manager directly informs the device here to do so. And then the device updates its CDAT tables, which causes an interrupt to the host, and then the host releases that memory. Rises the traffic on that port, releases that memory. And likewise, the memory gets assigned to H1 when the CDAT tables on D2 get updated for H1. Now, the idea here is we don't disrupt the traffic while these things are happening, and it should also use the existing Linux memory hot plug mechanisms or anything which is existing in the ecosystem today. Now, this is memory pooling. What it basically helps us achieve is that we can utilize the memory efficiently and save the PCO. Global fabric attached memory, this was something which Sridhar covered earlier. I'm going to skip over this. This is a similar thing which Sridhar has talked about. Basically, what we are trying to enable here is having accelerators, having memory devices, and then enabling near memory compute. Now, coming to the challenges, what challenges do we see with CXL attached memory? Now, remember that this is something which is new. We have seen the CXL attached memory pick up in the last 1 year or so. The first challenge here is on tiering. Now, what do we understand by tiering? This is something which already exists. You have slow tiers, we have faster tiers. Your faster tiers are where, which is called the hot memory, where you keep in your pages which are very frequently accessed. Whereas your cold memory is one where you keep your bulk of the data which is not accessed as frequent. And in Linux, this is enabled using NUMA, non-uniform memory access. So even if you have a two-socket system, you actually see the NUMA domains for the processor memory on one socket and the processor memory on another socket. You can still see NUMA domains. And CXL is just a zero-core NUMA domain memory. When you have a CXL attached memory connected to a CXL capable host, you would detect it as a zero-core NUMA domain. And it is very important for the applications to take advantage. One should know the characteristics of that memory. So when you create a NUMA domain, you have your NUMA distances and all that information which is there, based on which you decide whether this should reside in that memory or whether it should reside in the remote memory. And it is very important that the device characterize their performance and we advertise the information in the CDAT tables. All this information is going to be picked up from the CDAT tables which are implemented on the device. So we looked at NUMA domains. Now there is a concept of page migration, active page migration, whereas basically if you have pages which are not in use frequently, you would move them to a slower tier. And that is something which we have lots of memory development kits using that mechanism specifically on CXL memory. Now, in the existing side of things, the challenge we have with the NUMA, the way it is implemented in Linux, is it actually always tries to assign, the memory management on the Linux tries to assign always from the native memory, because that's the node which is nearest to your CPU. So it always assigns it, and it goes to another tier or a remote memory only when the native memory is full. Now, in such a scenario, what can happen is you exhaust your native memory allocations and you spill over to a remote tier. But there are chances that hot pages can get stuck in your remote tier, which will impact the performance of the application adversely. So what we need are smart mechanisms which can actively migrate your pages, which can actively migrate cold pages from here to a remote slower tier. And if there are hot pages here, to bring them back into the memory which is closest to the CPU. And there is a lot of work being done in this area. There is an implementation from Meta, which is part of the open source. If you Google for it, you will find it. The patches are all open source. So that's one thing. There are also development kits, I think SMDK from Samsung, which also does something like this. Now, what do we expect? Because this is an initial deployment of CXL, we don't want applications to change. We want all this to be done transparently. We want the active page migration to be done under the hood. We don't want to modify applications, the standard applications which have been working, just to be modified to use a slower tier. That's the goal actually. And contributions in this area. I mean, this is one of the challenges, and contribution in this area would be really helpful. Now, coming to deployment challenges, when we start deploying CXL attached memory, so the first thing we would see is how do we do error handling in CXL. The goal when we define the error handling specifics in CXL was to keep everything aligned and to be able to reuse the existing RAS mechanisms which we have. So one is poison. Poison is basically to be treated how we treat poison from a native DDR. So we already have the infrastructure in place to handle poison. Next is viral. Viral is basically an uncorrectable fatal error which renders your unusable. Now, this also is we already have infrastructure in place to handle fatal errors like in PCIe. So this can also use the same thing. The category where we differ or we need more developments from the ecosystem is in the CXL protocol errors. So CXL protocol errors are indicated via PCI advanced error reporting mechanisms. There are additional CXL RAS logs which are defined. So we definitely need software which is aware of CXL logs. It can go retrieve the logs from the device and do take the action appropriately. Then we also have CXL component errors, wherein we have architected a component command interface in the CXL devices, where we use a particular record format to report all these errors. And the way we have two ways here. We can do a firmware first mode, where we use the vendor defined messages to report the error, or we can use OS first mode, wherein we use the interrupts, MSI or MSIX, to report the error. Now, we definitely need development, software stack development from the ecosystem to handle this scenario. Next is quality of service. Now, when we have memory clearing, which is what will happen with CXL memory deployment, we basically need to be aware of the quality of service so that we can allocate the right jobs to the right memory. Now, here is where in CXL 2.0 spec, we have added indications wherein the device can indicate its load conditions, whether it is severe, optimal, or low, or the medium to the host. And the host can use rate metering mechanisms along with the QoS indicators from the device. What we need from the ecosystem is the devices to be implemented to support QoS so that the host can regulate the traffic, or it's basically a feedback mechanism, can take care of the loading of the device based on QoS. Then we have lifecycle management. So as with any other device, there is a requirement for lifecycle management. Now you can have firmware events, you can have RAS events and thermal events, and you want to do a device health check. These are all the things which are needed as part of your the deployment of the device. Now at runtime, so you may want to do a swap of the DIMM. So you have to read out what are the specifics of the DIMM. And all the infrastructure is orchestrated in the CXL 2.0 spec. So we provide a command interface wherein one can read all this information from the device. What we need is the infrastructure on the ecosystem side, on the software stack, to be able to understand and decipher this mechanism and keep a track of it. So there is a lot of software ecosystem development which is required here. And then security, the best thing today. So we do support the integrity and data encryption on CXL link, which takes care of interposer attacks. But we don't have anything for addressing confidential compute requirements, which is basically securing the data while it is in use. There is a work group which is working on defining security tenets for confidential compute. We would like more participation from everybody to enable that.
TDISC also supported on this?
Which one?
TDISC. IDT device. Sorry.
No, we don't have that support right now. In 2.0, we introduced CXL IDE. We are working to define advancements or enhancements to security side of CXL. There is a work group which is already working on it, keeping in mind the confidential compute requirements. So in summary, we have CXL attached memory used models which are continuing to grow. We are going to see more deployments of CXL-based memory pooling. That's the one which is going to become more popular this year. And as a consortium, we are continuing to address the challenges, but we would also like a lot of support from the ecosystem and from all of you. There are a lot of opportunities ahead to do enhancements, and request you all to get involved with CXL consortium. And with that, I will end my talk. Thank you for attending the tutorial.
We have this host and device master, right? So usually in PCI you can have the same thing can be configured as a host. So is it the same applies for here as well, like having the same IP being configured as a host or a device?
You can design your IP to be a downstream port or an upstream port. Now, what you need is much beyond that, right? You also need, if you want something to be a downstream port, it can be a switch downstream port. In that case, it's simpler. If you want it to be a root port or a root port on the host side, you need additional infrastructure for CXL, like the home region. But you can definitely design your transport layer to be either upstream or downstream.
So it's like if I have a two same identical source and I have the same thing and I want to connect and try to do the same on a front-end way. So it is possible at hardware IP to configure one as
design your hardware IP. See, that is something which will happen at the link up time, right? So you can configure. Eventually your IP has to be configured before the link training can begin. Right?
It would see if I want the implication of this thing. So
So you don't duplicate the data. Concept of deduplication was if you don't do sharing of memory, you will end up duplicating your data. And what does deduplication mean? When you enable sharing of memory with CXL3, You want to wait your recap. That's what it is.
Please raise your hands if you have a question. I can bring them. One of us can bring the mic to you.
Hi. Does the protocol support dropping of packets?
What do you mean by dropping of
So
packets?
let's assume that there is a host state and device 1, 2 and connected over CXL. Let's say there is an invalidation message coming from the host to the device, say, and it sends a message. And let's assume that the other two are busy. And is there any scenario under which the message gets dropped?
See, in that case, what would happen? You have issued a snoop from the host, right? And the host is expecting a response from it. If you're going to drop it, your host is going to time out. And it would lead to an error because you have not received response for the packet which you were expecting. It's a reliable protocol. We don't want to drop the packets unnecessarily.
So the hardware expects it to be reliable. Okay, then I have a connected question. In the first session, I had seen that there is a dynamic mux there, when which the protocol usually can operate between the IO mode or the CXL accelerator.
Yes.
Now, let's assume device 1 is in, let's assume there's a piece of data that is already on the host cache, and that is also shared to device 1 and 2. Device 1 is in IO mode right now, and device 2 is in the CXL cache or memory mode. And let's say the core writes to the cache and wants to invalidate, so basically wants to take ownership. Therefore, the invalidation messages goes down to both of them. So currently, when it transfers, it will be in the buffers, right? Yeah, and if it doesn't respond in time, it basically times out, creates an error. Now my question is, now there are, let's assume the first is invalidating or trying to invalidate multiple cache lines. So that will generate multiple requests and they will get queued. So there is a cost we are paying when it comes to performance of the cache itself for the cost. And what is the kind of penalty that have we observed that?
See, when you definitely the snoop invalidate going to a device which is off the chip, you are going over a link. So it definitely has a latency penalty compared to when you are operating on the chip. So that is given, right? The idea here is to reduce this. And if you recall what Sridhar had mentioned, was by design, the transaction layers are designed for minimal latency because we are dealing with fixed size packets. Unlike PCIe, we are not dealing with PLPs which are of different sizes. Here we are dealing with fixed size packets, which means your implementation can be very latency sensitive. You can design it for lowest latency. Now, the goal here is, of course, you go off the chip, you are having a bit on your latency. The idea is your latency should not be worse than when you go across the socket. So you still do, right? In SNP applications, you still have multiple cores. Data can be with other cores cache. Your job moves to the previous core and you may want to go and invalidate that cache. You still incur latency there, but you're still on the chip. The idea here is with CXL, we don't want to see a latency which is much worse than that. That's the goal.
So, final question. So, when designing the CXL standard, when defining the internal router network that carries these bits and the further packets, is it up to the designer to design the buffers for the CXL protocol?
It's a credited mechanism. It's a credit-based mechanism. So you advertise the credits, the receiver advertises the credits to the transmitter, both sides. It's a credit-based mechanism.
Basically, the cache will come to a card provided the device.
Yeah, if there are no credits, things will stop, right?
Thank you.
First question, so when we get a wider layer, in a system where you have a switch and all ports and all devices, is it like particular host to a particular device is kind of that linkage down, or is it
Only that device will be done. The whole idea of viral, the first thing which you do when you see viral is isolation. So you basically requires all transactions to that device which is indicated by.
how does it communicate to other devices from which want to communicate with this device?
Yeah, so before the switch, in 2.0, the viral will go to the host and the responsibility of host to isolate that device. with future generations, the switch knows that this is viral and that is communicated across the devices. So basically, the switch will isolate that device.
Just in the credits that you said. So if I am having like a post and link file, and if I'm credits are exchanged between those two, but in this multi-system, how is the credits being exchanged?
Credits are always for the board.
Are there any reference IPs for these protocols?
There are companies developing CXL transport layers. So you can see companies like Rambus, Marvel coming up with their implementation performance. Yeah, it's too early for it to do.
Yeah, apart from the spec documentation, is there any other good reference manual that we can look into?
Not in terms of documentation, but we do have a lot of webinars research for them. Those are really good.
So they are open.
The documents are-
Let's say if I want to develop a custom IP in this interface, is there any resource available to the academic friends?
Not at this point. At least I have not. It takes time. It will take some time to come to efficiency. Because it's a very relatively new technology.
I mean, when it comes to the standard itself, is the standard available to the point where we can implement it?
Oh yeah, there are the standard is available. There are post implementations available, which you can actually support CXL.
If you can refer me.
I have one question.
Sorry, no.
So PC supports this traffic classes, different traffic classes. So in CXL, MEM or cache, do you think there's a use case for it, or is it only a single build?
We do not have concept of traffic class defined there, but we definitely have different QoS channels based on LDIs.
Meaning at the memory level, do you think everything would be in the physical layer, it would be at the same for the data link layer? The priority. For PC, you have different traffic levels. Similarly, would there be a use case for the CXL MEM?
So see, CXL MEM is only providing you an option to connect from host to a remotely attached memory. The media behind is again, it could be anything. And how that media connects to the device is something where the designer connects that media. But the CXL does not tell you how to attach that media. The CXL only tells you how the host should access that memory, how the memory is connected, what kind of memory is connected, whether it supports meta bits, whether it supports traffic classes. CXL does not define that. That's up to the device to connect.
In case of a scenario where a device is very highly utilized and a remote chance that it may go out of credits, and we don't follow out, right? We don't follow out. How is this supposed to be handled from a protocol standpoint?
So you have a memory device, it's running out of clearance, which basically means that you are loaded heavily. You are not able to respond in time, right? In that case, your traffic would slow down. Either there will be a back pressure which will build up ultimately in the
How is
system.
this back pressure? Because there's no ordering on it, right? So
The credits are still there, right, in play. You won't return the credits. Right? You may receive your transactions. For the transactions which you have received, you will return the credits. But ultimately, at some point, if you're not able to, if the device is not able to provide the responses back, it's going to backfill, right? All the requests which are there are going to start getting queued, which means the queues which are on the receive side on the device are going to start getting filled up, which will eventually translate to a back pressure on your system because you will not be able to release the credits at some point.
any research group or anything,
Yeah.
so everything will be back pressure.
If there are questions from the other room, please funnel it through. Shika from. Of course, we can continue taking questions here.
What is the difference between AMBA?
Okay, one of the questions is what's the difference between AMBA protocol and CXL? So AMBA protocol is a specific protocol for coherent implementations. CXL is basically trying to define a coherent link with the devices. One can always use CHI, AMBA CHI for connection to devices, and that's what exactly the C6 protocol did. It was channeling CHI package onto the devices. So one could use, but not on CXL. CXL has its own defined formats for packets, and CHI could still be used on the host side to maintain the coherency. So in fact, that's what most of the ARM systems do. They use the CHI protocol internally for maintaining coherency.
Only one question. So
you talked about fleet between them. So what is a fleet actually?
The fleet is basically the unit with which the data is transmitted. In PCI, you can deal with TMPs, when your data your packets. In CXL, we have bits, what we call it. And they are of fixed size, 68 bytes or 56 bytes. And that's what we use to transfer this.
Usage of or CXL. Is there any protocol changes or updates?
Shika, any questions from 1403?
The PCI protocol is definitely evolving.
Can you hear me?
And 6.4 is actually moved to a based format. So there are changes happening there. There are another rights which are added. There are protocols are developed on both sides. And
But anything specific from CXL we added.
the split idea is basically shared between these two. First started with CXL and then PCI set up.
So for PCI will say compliance, so for CXL also any.
Yes, so CXL consortium also runs FYI compliance events for the devices and the hosts which are out there. I think we have one compliance event coming up. It's not as big a deal as the PCI SIG compliance at this point, but yes, there is a compliance suite for CXL.
We have this point-to-point CXL. So assume you have a host devices and you have two memory type serials that connect, and each type 3 to the switches, assume it's a 30 data transactions per second, and when it goes to the individually there are 32 and at the top it's only 32. And assume that one is being consumed heavily. So how does that get the QoS at the top layer? Is it like Y2 that it gets translated as that only latest